This is BhamQuants, and we're going to do a linear regression in Microsoft Excel. First thing I want to point out is what are the requirements for a linear regression. There are 5 requirements I've listed here. The variables you use must have a linear relationship, hence the reason it's called a linear regression. It needs to be multivariate normality, which means that each of the variables that you're going to look at have to fall within a normal curve. There is no or little multicollinearity, so my weight in pounds is related to my weight in kilograms, and so those things are related. That is not how you're supposed to do a linear regression. No autocorrelation. So autocorrelation would be the temperature today is related to the temperature yesterday. That's not how you're supposed to set up your variables. And finally, it's supposed to be homoscedasticity. And what that means is the variance in a with the small time series is the same as in the large. So the probability that I'm going to have a stroke while presenting to 15 people, the standard deviation of me having that stroke should be the same as the standard deviation when I'm presenting to 1,000 people. So it doesn't matter where we are in our series, 15 people or 1,000 people, the standard deviation is the same. Let's go get some data. We're going to go out to the website Kaggle.com. Sign up for it, it's free. Apparently I need to sign in. There we go. And we're going to search for the data set, weight, height, and here's my data set. And I could go right here and download it. That'd be perfectly fine. But rather than do that, I have already done so. This is my data set. So we have gender, height, and weight. I want to predict my gender by using my height and my weight. So the first thing I'm going to do is add a column. I'm going to just gender underscore number. And if it's male, then give me a 1, otherwise give me a 0. So the men are 1s, the women are 0s. This is going to be a binary solution, which is not going to be as clean as a continuous solution, but we're still going to see some groupings around the 1s and the 0s. We have height, we have weight, and I want to add another variable for the sake of argument. We're going to call this random, and this is going to be a random variable. So my prediction is that gender is probably related to your height, it's probably related to your weight, and probably has nothing at all to do with some random variable. So let's see what happens when we run this regression. The first thing we need to do in Microsoft Excel is go to File, Options, and we need to go to our add-ins. I'm going to go ahead and click on the Excel add-ins, the Manage It, and what I want to do is click on the Analysis Tool Pack. Now, because I work in Excel for a living, I've already selected the Analysis Tool Pack, but you need to select the Analysis Tool Pack in order for this to work. So we have the Analysis Tool Pack loaded. We're going to go to the Data tab, Data Analysis, that's what the Tool tab gave us, and we're going to do a regression analysis. Okay? My Y ranges are my gender. I'm grabbing the header name. Come on. There's my gender. My X ranges are these 3 variables right here. I have included labels in my X range when I selected my data. We're going to click OK. This gives us a Anova table. So the the adjusted R squared tells us that approximately our Y values, our gender, is about 65% of that Y value is explained by using our variables. So that's decent. We can look at our F-stat and our significant F-stat. So in this second section down here in Excel, we're looking at the regression as a whole, 1 unit. As a whole, we have an F-stat of 6,000 with a significance of 0. So the significance is the tail end of the distribution. And so we're saying that as a whole, this is fitting, our X values are fitting our model really pretty well. Now, rather than look at the regression as a whole, let's look at the individual parameters of the regression. We have an intercept, the height, the weight, and the random. Let's look at our p-values. So the intercept, the height, and the weight, the p-values are very small. Again, that's the tail of the distribution. That's telling me that's a really good fit. Look at our random value. Our random value is terrible. Our random value, statistically telling me, is not related to the gender that we're outputting. And so we want to throw that away. Now, I can't just throw that away and say I'm good to go. What we need to do is to actually throw that away. So let's go back to our original regression. And we're going to do another regression. Data analysis, regression. Our y values are the same. Our x values are going to change. We're going to throw away the random because we already determined that that had nothing to do with the gender. So now we're just going to look at height and weight. The labels are selected. Click OK. Our adjusted R is still 65%. Our model as a whole is still quite good. If we look at our p-values, every x value that I've dealt with is now significant to the distribution. So we're going to call this good. So let's come over here for the sake of argument. The intercept, the height, the weight. So the intercept is this value. The height is this value. The weight is this value. Let's test it. And so we're going to go with me. And so my intercept, we're just put a 1 there. My height, I am 74 inches tall. I will go ahead and tell you I'm 220 pounds. We're just going to ignore that. And we're going to do a sum product. That, comma, that. And I am a 1.8. Kind of looks like a male. Let's do a female. Let me point someone out in the audience. No, I'm kidding. The intercept is 1. The height, let's make her 5'6". So that's 66 inches. Height, 150 pounds. And oops. Oh. Have to lock my references up here. .32. That kind of looks like a female. Okay. That's how you do a regression in Excel. Let's look at my solution. This was done on a similar but not identical data set. We talk about the adjusted R-square shows that 65% of the Y, 65% of our data is explained with this regression. The F-stat says that the tail end of the curve is here, essentially 0. So this is a good predictor as a whole. When we look at the p-values, let's look at a graph of p-values. The p-values are these tail pieces right here. And so we want those tail pieces to be very small, saying that we're in a very good, it's a very good match, each one of those individual pieces. And so at the risk of having done a terrible job of explaining the statistics, because I do not do that every single day, that is how to run a regression. Be sure to pay attention to the requirements of a regression. You can get yourself in trouble the further away you stray from those requirements.